Good morning. Good morning. This is an exciting day as we're kicking off this Carbon Hub. And we've got an exciting panel to start it off. So first I'll briefly introduce myself, then introduce the panel. Then they'll each make remarks for about 10 minutes. And then we'll throw it open for 25 minutes for questions from all of you. So that's it. By way of introduction, my name is Hugh Helferty, and I'm on the advisory panel for the Carbon Hub. My background, I spent over 30 years with ExxonMobil, and the first half was mainly spent in refining, where I was making the fuels that we burn every day to put carbon dioxide into the air. The second half was mainly in research, and I headed the Petroleum Products Research Organization. I also headed the Global Chemicals Research Organization, and I headed the Corporate Strategic Research Organization, which is really the fundamental sciences lab for the whole corporation. And so it was through that I got a picture of what we were trying to do to help create some of the future. And we were in corporate strategic research, we were doing a lot of work and looking at alternative energies and what we could do to contribute to that. I retired from that almost exactly 5 years ago. I now teach a course called Science Leadership at Queen's University in Kingston, Ontario in the fall, and I enjoy my winters here in Houston. So we have a panel here, and the topic is Energy Transition and Opportunity for Hydrocarbons. And we've got three great panelists. They are Scott Nyquist, Senior Advisor at McKinsey and Company, Bryan Pivovar, a Senior Research Fellow at NREL, and Marc von Keitz, a Program Director at ARPA-E. So that's the extent of my introduction. They'll each have 10 minutes to speak, and then, as I said, we'll throw it open for questions. Scott, will you lead us off?
Trust the system.
Trust the system, she says. Okay.
Your slides are coming up.
Okay, I'll start talking and then they'll come up. All right. What I'm going to do, first of all, thanks for the opportunity to share our views with you. What I'm going to do is provide some data and analysis from McKinsey's Energy Insights team, in which they every year will go and do a bottoms-up analysis, every country, every sector, every source of fuel, looking at the future of energy over the next several decades. And I'll describe some of their kind of key analyses that they've done. But before I do that, I just want to give a few summary messages from that work that I think is relevant to what we're talking about today. I mean, the first message really deals with overall energy, and it deals with what we see as the gap looking forward. If you compare to what most energy forecasters say will be the future of energy supply, and compare the greenhouse gas emissions that will come from that energy supply compared to what climate scientists say are acceptable levels, there's just a huge gap out there. We haven't found a way yet to meet the aspirations of climate scientists. So we're going to need more innovation if we're going to be able to reduce that gap between what climate scientists say we need to do versus the direction we're currently heading. So that's message one. Second message, if you look at hydrocarbons specifically, and then within that, crude oil, we anticipate that crude oil demand will peak and then decline. In fact, many regulators around the world want it to disappear altogether and are working hard to get rid of it. And if you live in Houston or Texas or involved in the oil and gas industry, this is not good news. We need some big ideas to find new ways to use this amazing feedstock for the future. So this group is about innovation, and we need some big ideas to help on climate change and help define the future of the oil and gas sector as well. So let me just share some data, and I'll start off with the global view on power generation. And what this chart says is two big messages. One is that we're anticipating a very robust growth in demand for electricity around the world, driven by air conditioning in Asia, new appliances around the world in developing countries, and new uses for electricity in developing countries as well. So very rapid growth in electricity demand, doubling of demand. Very rapid growth of renewables. wind and solar in particular. And through those renewables growth, we expect that power generation from renewables will be more than half of power generation supply by 2035 and more than 70% of supply by 2050. So we're very bullish that renewable economics will continue to improve and they will effectively take over the power generation supply, which is very good news from a greenhouse gas emissions point of view to have all these zero carbon sources of power. Now that's the good news. The bad news is that power generation is not the only source of energy demand. We have the industrial sector, we have the transportation sector, we have residential, commercial that use energy other than power. And when you do the same analysis looking out decades ahead, you find that some 65% or more of energy supply will come from fossil fuels. So despite rapid renewables growth, even at as high levels we can imagine being practically implemented globally, you still end up with a fossil fuel dependent economy. And then if you say, well, what does that mean for greenhouse gas emissions? In this scenario, we look at greenhouse gas emissions peaking in the next 5 years or so, and then declining, which is good news, out to 2050, about a 20% reduction in greenhouse gas emissions by 2050 in this reference case scenario. But if you look at the lines here that are for the 2-degree pathway, or even more importantly, the 1.5-degree pathway that the climate scientists say are required, you see this huge gap between the direction that analysts would say we're likely to head given current technology, current regulation, versus what the scientists say we need to deliver. So this is the challenge. You all have to come up with some big ideas to close that gap. It's going to require innovation, maybe a bit of regulation help along the way. Let me now just talk about oil demand. And this chart looks backwards 30 years and then forward another 30 years. If you look over the past 30 years, oil demand growth has been remarkably consistent at 1.2, 1.3% per year growth over the last 30 years. Very stable growth, and this is driven by population growth, driven by GDP growth, as wealth around the world has continued to expand. Going forward, we're anticipating some significant changes to that growth, slowing growth this decade and then peaking sometime in the 2030s, and then declining thereafter. This is due to more efficient use and then substitution of electricity and transportation and substitution of gas and other uses. So we have a view that oil demand will likely peak and decline. Now, there are many scenarios out there, and when we talk to regulators around the world and corporate leaders in industries other than oil and gas, they always ask, well, how can we reduce hydrocarbon demand even more? What are the possible scenarios you can imagine? And so our team, as many creative analysts come up with, you put in this particular regulation, this is what would be the impact on demand. And if you put in more aggressive regulation to encourage electric vehicles, you can knock out another 20 million barrels of oil demand by 2050. If you accelerate the pace at which you do recycling in plastics, you can reduce another chunk of demand. If you accelerate innovation and regulation to support biofuels and electricity and gas in marine and aviation, you can knock out another chunk of demand. And this is what regulators around the world are doing. What can we do to find ways to eliminate oil and gas demand, in this case oil demand, in the future? And this is on their radar screen. And one of the interesting things is that every time we do this analysis, we've been doing it for 20 years, what you find is the outlook for oil demand goes down every time we do the analysis because you see more action taken around the world to reduce the demand. So, 3 simple messages. We've got a big gap to work on to reduce greenhouse gas emissions. Hydrocarbon demand is declining, which is not good if you are thinking about wealth creation in Houston and Texas and our economy and the oil and gas industry. Need big innovation to come up with solutions to both. So I'll stop there.
Absolutely. So I'm Bryan Pivovar from the National Renewable Energy Lab. I have been a major component of putting hydrogen's increasing role in the energy system on the map across the national lab system and within DOE. I led the original hydrogen big idea that became hydrogen at scale. And I'll mostly talk about how hydrogen fits into what the Carbon Hub's mission is. A lot of this is driven from the megatrends that are changing on the planet now, and that'll likely be my first slide. Basically, we have these different issues going on. Renewable energy is getting cheaper. I'm really proud of a lot of my colleagues at NREL who've done a great job of helping drive down wind and solar costs. That's not what I do. That's leading to different policy. The talk before me was great in terms of setting up kind of the mission space for this. And also, you could see that what happens is that the grid tends to take up things like wind and solar, but we have this cross-sector concerns, and that's actually where hydrogen comes in and can play a big role. You're seeing energy policy, and you're seeing this drive for increased electrification as the cost of wind and solar have come down in the last decade. Basically, purchase price agreements have dropped from things like 10 cents a kilowatt hour down to 2 cents a kilowatt hour for wind, and maybe something like 14 or 15 cents down to 3 to 5 cents a kilowatt hour for solar. It's making renewable electrons the cheapest electrons on the planet, but there's an issue with their intermittency and their variability and how that fits into the entire energy system. So I'm a hardcore PhD chemical engineer, material scientist, and I've spent more than 120 hours of my life putting together graphics like this one, right? I never thought I would spend as much time on one graphic as this one, but it really comes down to how we basically talk about different energy sources moving in different ways. We laid this one out kind of like a Sankey diagram, so where we get our energy from is on the left side, things like renewables, nuclear, fossil. And those typically go to the grid, which is one of these big infrastructure circles. We also have this other big infrastructure, which is the natural gas system. Hydrogen has a way to couple those. So you can take the electricity, you can make hydrogen, or you can take things like methane and make hydrogen, which is the way it's done now, through SMR and just jettisoning a bunch of CO2 or generating CO2 streams. You could also obviously take it and reduce it to make carbon blacks or hopefully better value products. I'll talk a little bit quickly about some of the different areas and how I think about hydrogen and how it relates to carbon. I work for the National Renewable Energy Lab. I'm glad that natural gas has become so cheap and abundant because it's a great gateway along this pathway for how you can economically get hydrogen into the system in different ways. So if you had hydrogen, you could bring it back and put it back into the grid. But really what you can do with hydrogen that's really unique is you can store it for long times and you can move it into things like transportation and industry or building heating. But you start with the highest value propositions and work your way down from them. So what I wanted to make sure a group like this understood is kind of all of the action that's going on in hydrogen currently. So there's this presentation that Sunita Satyapal, who's the Fuel Cell Technologies Office Director, gave at the HTAC meeting, basically goes across all these different areas where you can see all of these different governments, industrial institutions, pursuing roadmaps for how hydrogen will have to build out and what it will do in this situation. And then where hydrogen currently sits. So currently there's a 0.5 gigawatt of stationary power, and these are just US numbers, these aren't global numbers, but 0.5 gigawatt of stationary power, over 30,000 forklifts. If it's the one really economic place for hydrogen today. If you own an Amazon or a Walmart distribution center, you run it on hydrogen-powered forklifts. I can go into details on why that happens. There's buses, there's cars, there's retail stations in California. And when I started graduate school on fuel cells 25 years ago, one of my roommates said, "You've chosen wisely. Hydrogen and fuel cells will always be 5 and 10 years away." And that was actually true until 5 or 10 years ago, right? The Hydrogen Council, which a number of the industrial members who are here are part of, is really a huge advocacy group for this. In November, they released a US study led by McKinsey, and McKinsey also set out the worldwide one that was based on 2050 as well. So you'll see some startling numbers, things like, in just the U.S., $750 billion associated with it, 14% of all energy running through this. The one for the world was actually 18% of all of the world's energy. So you'll see these numbers in terms of jobs, in terms of energy, and basically this is a way to basically run clean. And when I say clean, it's CO2, but it's also local criteria pollutants. And a lot of times that's the bigger political motivating factor. I like to say the reason that India and China are in the Paris Agreement have less to do with global temperatures and more to do with breathing the air in Mumbai and Beijing. So I mentioned that I'm a hardcore chemical engineer, and I think that this is another slide that I put together. Typically when I had thought about fuels when I was a PhD student, I thought just in terms of the delta G or the delta H, so basically how much energy there was per molecule. I've become an electrochemist over time, and now I think of energy more in terms of potential per electron. And so if you look at that second column there, I can relate these energies that are available in different types of bonds. So you can compare things like hydrogen-hydrogen bonds, carbon-carbon bonds, carbon-hydrogen bonds, and nitrogen-hydrogen bonds. And then like fifth line in this table is actually steam methane reforming. And so when I think of methane, I think of something that has basically 8 electrons to liberate energy with. If you stop short, but what it comes down to in this is that the hydrogen-hydrogen bond has slightly more energy than all of the other bonds. The carbon-hydrogen bond, the carbon-carbon bond, or the nitrogen-hydrogen bond. A lot of times it's the easiest one to get to. So from taking electricity and going to chemical bonds, it often tends to be the right pathway. Looking the other direction, you can look at methane, and you can say, if I stop taking out some of these bonds, what else can I do? And I don't have carbon-oxygen bonds or anything else there, but whenever you further oxidize something, you take away some of its energy. I know that a lot of the talk will be about straight carbon, solid carbon products. When I think about using fossil for hydrogen generation, if you stop at 4 electrons, you're only getting half of that, which is why we take it all the way to CO2 and liberate as much as we can from SMR. If you can find out ways to go further oxidized, I think of things like fabrics or synthetic wood or other parts of the materials that would fit into the energy system. A lot of times we'll stop on carbon because of its tensile strength or because of its conductivity, but there's a bunch of different things that could go further. If energy release is one of the issues, trying to get the hydrogen out, you may want to further oxidize it. The last 2 slides are just NREL. If I don't include these, they don't let me travel. We work with most of you. We understand a lot about energy systems integration, and we're building national facilities to basically help enable these types of processes to go on. And with that, I just want to thank you for your time and appreciate the opportunity to come and talk.
Okay, so my name is Marc von Keitz. I'm a program director with ARPA-E, and about 3/4 of my talk has already been said. So I'm trying to skip through a number of the presentations here. But ARPA-E, to the people that don't know it, we're part of the U.S. Department of Energy and have been around for about 10 years, which incidentally overlaps quite well with the natural gas boom in the United States. And so one of the questions that we have been asking ourselves actually repeatedly over the years is how can we maximize the benefits from this tremendous wealth that exists in the country? And so we have over the years done a number of different programs that are trying to leverage this to, on the one hand, make energy cheaper, but also to really drive down the associated emissions. So I not have the time to go into any of these, but one of the things that came more recently, actually very closely connected to rice. Sergio, we had conversations here at a meeting back in 2016, and then it percolated into methane pyrolysis that is really revolving around what we can do with methane. And as was said before, about half of the energy of methane sits in the hydrogen portion. And we are already broadly taking advantage of that through SMR, and there we actually go even a little further by fully burning the CO2 portion as well. And it's a very effective process, well designed, but has a little bit of a problem that we still have significant CO2 emissions associated with that. And so are there other ways to deal with that? And so most people in this room may be familiar with methane pyrolysis. You really, at elevated temperatures, break the carbon-hydrogen bonds and generate a solid carbon product that can take a lot of different forms. But the key element is that you really need to look at, it's basically in some form a pre-combustion carbon capture opportunity that you have there. And so while we are talking a lot about CO2 capture in the conjunction with SMR, and then here in Texas you probably have enough oil fields that you can stick the CO2, but there might be issues in other geographies and other geologies where it's much harder to find appropriate opportunities and where you can store things safely for long periods of time. Solids are much easier. So that's definitely an opportunity. But once again, you have to arbitrage between the ease of potential storage and the price you pay for getting a reduced yield of hydrogen from your material. So what that really means is that, well, storage is kind of maybe the simplest solution, but maybe that carbon is too valuable to just store. And finding ways of dealing with that is I think really an important opportunity. And this is just, it's a very much back of the envelope calculation, trying to see what, if we only try to pay for, and this is more from a BTU energy burning perspective, that we're looking at if instead of methane, we are burning hydrogen, and we are, in order to make up for the difference in BTU value, how much would we have to get for the carbon? And so it's very much a function of the base price of natural gas. So 2, it's a very extreme low end, but at 6, about 187, well, let's say a little under $200 is what you would probably need to pay per ton of carbon product in order to make up for the this is not taking into account that hydrogen tends to be more valuable than methane for certain applications, but that's just to give things a little bit of a perspective. So it's in an interesting range when we look at this classical curve. The other part, okay, so we are in a range of prices that is not too high, and what this is really interesting, it allows us to get into a range where the markets are large enough. Because if we are talking energy, the markets are tremendous. The amount of carbon that is just stoichiometrically to make the equivalent of 1 quad of hydrogen, you generate 22.4 million metric tons of carbon. So that is a very, very large area. It's like 2 football fields in an area in a cube, basically. So the question then really is, if we want to capture value from this material, we need to push into application spaces that are large enough to absorb these volumes. And so what we have done at ARPA-E is we have been looking at this question, and so how do we want to get into this realm? So there's 2 ways. You can either see, is there a way that we can do this even cheaper than SMR? So it's like brute force, just focused on hydrogen, and we just kill it based on the process efficiency. And the other part would be to look at it from the perspective of just how can we maximize the volume, the quality of the carbon product, and then see, do we find new applications for that? And so this is a summary. We started back in 2017 to fund through various means a combined cohort of now 8 teams in the carbon space. And so the focus here is, as I said, hydrogen generation, carbon generation, and then there's one aspect of carbon upgrading that is in there. Let me just quickly go the hydrogen focus. You really want to maximize space velocity, really get the catalyst life as long as possible. And you still want to have a carbon product that at a minimum is not contaminated. You don't want to pay for this. You don't need to have to put it into hazardous waste landfills. So that's really an important part. The other end, and this is where some of the people here at Rice clearly come in, there's really opportunities. How can we make high-value materials that are of defined properties? And there it's more an issue, how can we not only scale the markets, but also the technology, because a lot of these technology work well on a small scale right now, but once again, to make it relevant for the energy scale, that is really what we call the ARPA-E hard challenge on a technological side. So the one thing on markets, we have one project, and I wish I had a little bit nicer graph on that, but we are funding a team centered around MIT, an architect that is looking how we can incorporate these advanced carbon materials into building structures, because buildings are really one of the largest volume absorbers of materials in the world, and they are still continuing to grow with the urbanization and population growth. This is definitely still a growth sector. And if we can actually, it's not only that we find a home for the carbon materials, but it also is a tremendous opportunity to displace some very energy intensive materials like concrete and steel. And so with that, thank you.
All right, I'd like to thank our speakers for some great introductory talks here. And we have about half an hour for a Q&A session. So maybe I can lead off with one question and then turn it over to anyone in the audience. I believe there are going to be people, Marie, you have a microphone, so if someone has a question, we can turn it over to you. But maybe I'll direct my question to Scott, although the others can jump in if they wish. You know, there's a lot of talk, of course, about the electric car as the part of the solution to the climate change issue. And, you know, some in the public naively kind of think, well, if we have an electric car, we have a zero-emission vehicle. But, of course, it all depends on where the electricity comes from. But what I tend not to see much in the literature and what I read about is the kind of scale of electricity that would be required in order to convert a substantial portion of the fleet into electric cars, and the feasibility of that both from the standpoint of electricity generation and transmission. So I wonder, is that something that you or some of the other organizations have studied and can help to put in perspective for us so that we understand that?
Well, I would just make two comments. One is that I think we were surprised at just how little energy it really requires to drive all these cars. I mean, it turns out that air conditioning and lighting and heating are enormous consumers of electricity, and the automotive sector, even if you make big shifts toward electric vehicles, isn't that much of an add. And so when you couple that with the second message, which this has to happen slowly, because you have this 2.5 billion park of vehicles around the world that has to grow to 4.5 billion by 2050. And then you have to change all that to, it just takes a long time to make that change. So if you take the pace of change toward electric vehicles, and then you look at that it's not as much energy as you think to actually run these things, the system can adapt, is what we found.
Okay. So that's an
optimistic view.
Yeah. All right. Any other comments, or is that?
Sure. The electric vehicle is going to be great, especially for local air quality issues. I mean, so when it comes to urbanization and the trends for people to move into cities, basically electrified transport is really critical to improve the air quality in cities. They also is a connection to what you do with overgeneration. So all of these build-out models assume much more wind and solar, and what happens is by the time you get to about 30% penetration of these variable renewable sources, you start running into large curtailment issues. So you can see in a lot of the analysis that Scott was talking about that you're actually going to 75% of your generation by wind and solar. That actually spins into a different problem, which is what we saw at NREL, which is how I got voluntold that I was going to do something in hydrogen. It's that our wind and solar people were saying that the economics of grabbing wind and solar basically stop at about 20%. And the only way to get that to go further is to find other ways to use this energy. And shifting energy over distances and time, daily cycles and monthly cycles, and then across sectors is one way where battery vehicles help to do that as well.
Okay, good. All right. There's a question right here.
Yeah, this is a question for Marc. I would like to know a bit more about this collaboration with the MIT about carbon in construction. Could you speak a bit more about this?
Yes, I can. So this is actually a project that is being led by Marc Goldthorpe. I have to admit that we are not quite over the finish line with the contracting. I hope that it's going to happen any day now. But so they haven't officially started, even though they have done a lot of designs already. So the underlying idea is that they are looking into composite construction materials that are basically bringing together carbon fiber materials for strengths and then a polymeric resin in which these carbon fibers are embedded. And the underlying philosophy is that this enables not only more cost-effective materials potentially, but that you really enable new ways of building things faster. So you can do a lot of prefabrication, and then a big portion of the cost of construction is actually the time it takes to put buildings together on site. If you look at the financing structure, and that if you can cut construction time down from 6 months to 2 weeks, you have tremendous savings just on the financing side. And so that's, and then you have new design opportunities. Whenever you change materials, you get new design opportunities, and that's something that this project is trying to explore and leverage.
All right. Another question here.
Bryan, you brought up what could be a growing feature or a growing opportunity that we're likely to have far more times with surplus clean electricity as we get more and more variable renewables on the grid with more wind and solar. What do you see as the role that hydrogen can play in that? Because it's going to be potentially lots of cheap and clean power, but it's not happening all the time. How is that best used for making hydrogen or other power to gas? And then what are the best uses of that hydrogen?
That's a great question. And it comes down to, well, the economics will drive it in certain ways without policy, right? So transportation becomes the number one kind of play for it. And because it's zero emission transportation, it works well. After that, then you look at some industrial markets. It's the different places where hydrogen is actually made, so 2% of our energy in the country and basically globally goes through a hydrogen pathway today. And right now it's used to make ammonia, and it's used to upgrade petroleum. Those are two major markets that you would end up throwing this into first because they exist today, and you displace where you're making hydrogen from today. The other piece of this, and why hydrogen is so compelling, is the same duty cycles that are making the cars viable. The fact that you can have capital that only runs a certain percentage of the time and still make it economic, and you can basically turn it on and turn it off and have it last 15 years. Those are some of the, a lot of this is that we're trying to match generation and load together, and there's a mismatch. And then the question is what's the best way to offset those things while filling in all the other gaps we need? And so the beauty of electrolysis and hydrogen is they're large dispatchable loads that can fit that kind of profile, and then the hydrogen can go into the highest value applications. When a lot of times the people at NREL, when we talk about it, we say things like these low-cost electrons that are available are going to spill over into lower-cost hydrogen, and then the lower-cost hydrogen will spill across the expensive markets and into the less expensive markets as well, filling in certain roles where electricity can't do it directly. But there is going to be more electrified processes, but the intermittency and the variability, chemical bonds are just so much more energy dense and so easier to store for longer periods of time that hydrogen's not always the end point. Sometimes it's the starting point to things like ammonia or hydrocarbons as well along that pathway.
If I might just chime in there as well, one of the things that is actually in our ways, the intermittency of renewables can also be captured potentially in the context of methane pyrolysis by storing actually heat. So it's actually a very simple way of converting electricity into heat, even though oftentimes when in the classical way, when you start with fire, make electricity and then just turn it into heat, it seems like a big waste. If we have renewables, the equation changes a little bit. And so one of the opportunities that may exist, and I have pointed some of our teams in that direction, but we haven't really from the beginning actively put it into the metrics. But the opportunity is that you can, with renewable energy, generate heat that actually stores potentially cheaper than batteries. And it's a way to take advantage of that stored heat to then crack the methane. And it's a potentially more elegant way of actually accessing hydrogen just purely energetically than going through electrolysis, especially because the intermittency and capital utilization might be very different.
Okay, why don't we take one here and then we'll come there, okay?
This one's for Scott. This is one things like that. The one thing that I saw, and I don't know if I'm going to be laughed out of the room, but I'll ask it anyway, is fusion. Lord knows we've seen enough in the popular literature lately, but one thing that always concerns me about that is, and to steal a line of Bryan's, it may be the technology of the future and will always be the technology of the future. I'm just wondering what the perspective is on it, specifically since the economics of it. It's one thing to demonstrate it. It's another thing to worry about radioactive disposal or something like that. So where would fusion fit into this and how?
Yeah. Well, the way we did the analysis, and this is just for credibility purposes when we deal with various audiences, we only look at technologies that are working today and can be feasibly economic in the future. So even nuclear gets a bit of a hit because of the anti-nuclear thing. So we avoid the issue with that constraint. But that said, when you look out particularly beyond 2050, fusion and new forms of nuclear, modular nuclear are possibilities that you get very excited about. And what we find when we do our work, 20, 30 years out, you can kind of extrapolate from where we are today. But anything more than 30 years out, you have to be open to whatever possibilities are. So when we work with our clients on what's the post-2050 world, then all of a sudden everything opens up. So.
Okay, there was a question here.
Thanks. The role of hydrogen in the transportation sector, battery versus fuel cell, has fuel cell lost the battle already? And what's your view in general about hydrogen and transportation?
So no is the easy answer. But they're different, and there's different. Over the last decade have been remarkable, and now you can go buy them. They're still heavy and expensive relative to what hydrogen could be, but they're economically competitive. And if a lot of this comes to what the future driving habits are going to be and other types of things, like how long are we going to own our cars versus have different models. when, I've been on a number of panels with other futurists, and you get people from Lyft or Uber or some of these former transportation people, and, there's this drive towards transportation as a service. I lifted here, I don't have a vehicle, I just flew in, took a lift, and I'm going to take a lift back, and I'm not going to deal with anything. When you look at how drive cycles work, there's peaks for the rush hours, and then there's continuous. If we're sharing cars and things like that, that's a good hybridization system between battery-powered and fuel cell vehicle. There's also this issue about light duty versus medium and heavy duty. And so there's certain areas right now, so Nikola, which is the hydrogen fuel cell-based trucking company, is the one that's getting the most press probably. But when it comes to heavy duty freight and other things, the places like ports of Long Beach and ports of LA are going to be regulated out of internal combustion in 2030. The trucking operators are getting ready to do hydrogen, and they don't want batteries for much of their routes. There are times where batteries can fit that. The thing that I sometimes will quote is a Tesla supercharger, which is a really expensive infrastructure to basically try to move hundreds of kilowatts, and then they don't do it, at 100% efficiency, so they're still having to deal with heating problems that batteries don't like in those systems. Those charge at 6 miles a minute. When you fuel with a gas, you usually fuel at something like 150 miles a minute, and then hydrogen does about 100 miles a minute. So a lot of this is what's the duty cycle, what's the need of the equipment. There's a split, and there's a question about how big either part of the pie is going to be, but the different attributes of batteries versus hydrogen will have both of them playing in that space. Hydrogen has advantages at the heavy duty side, and batteries, if you're willing to charge on your home and drive limited miles over long periods of time, it's a great choice. And hydrogen can.
Just want to add to that real quickly. Just when McKinsey does modeling of this without really understanding the technology, you say that electric vehicles, kind of really own the small car market to start with, and hydrogen own the big heavy-duty vehicles. And then the question is how rapidly will the economics of hydrogen improve, and how rapidly will battery economics improve, and then who's going to win the stuff in between. And so if you're bullish on hydrogen, you can create a pathway to get it going, go down the learning curve, then it gets more of that market. And if it doesn't, then electric vehicles, you get more of the market. So we have some colleagues who say electric vehicles are going to blow hydrogen out of heavy duty, and they'll argue that, based on technology evolution. So.
This is for Scott. When you in OECD countries, Europe, US, versus the developing world, and some of these new energy sources of hydrogen and other things, you need infrastructure, even battery, even car battery electric vehicles. You're going to need a lot of new infrastructure. Do you see a distinction on uptake depending on where the demand is coming from?
Yeah, I mean, when these things get modeled out, embedded in them are all kinds of assumptions about regulatory interventions and subsidies to make these things work to go down, the learning curve. There's regulatory views embedded in the assumptions. And usually those are all starting with wealthy countries providing subsidies, Norway for electric vehicles, for example, and therefore the adoption gets higher, and then you go down the learning curve, and all of a sudden there's a point of which the economics of certain types of vehicles, for electric vehicles, are now equivalent to what they would be for internal combustion engine. And that's when you begin to see the adoption in these developing countries, because they can't afford economically to provide any subsidies to make these things work. So the big debate is, where's the economics crossover for each of these technologies, and the assumption being that low-income countries will not provide subsidies to make it work, with the exception of China, which has a different set of issues. But most of the countries outside of China are going to operate on pure economics, and they'll be slow followers.
Okay.
So I don't know where to direct the question, but Bryan said that SMR works only at large scale, and there's other options for making hydrogen. It'd be interesting to know what is the scale of a current SMR plant, and what is the scale, for example, the largest demos or plants that are being made with, say, water electrolysis, for example, and get a sense also of, and I don't know if Scott or Marc can help with this, in a situation where one wants to scale up aggressively, realistically, how much bigger is the next plant, and how long does it take to build the next plant, so that we could get a sense of how long would it take to match SMR, for example, in size.
I can take that on. So the biggest electrolysis plants that have ever been put into existence, there was two that were kind of in the 150 megawatt scale. They were, one is in Norway and it's associated with dams, and the other one is in Central Africa and it's associated with ammonia production. Both of them basically did the same types of things, and it's because they had either a need for something that was hard to get there, or they had cheap electricity that they didn't know what to do with. Those are both based on alkaline electrolysis technology, and they're basically ran 24/7 continuously. So they're not necessarily the same types of systems that would scale well with kind of the intermittency that we're talking about. So there's polymer electrolyte versions of it, and Siemens has a project coming out that's going to be, they have a 17.5 megawatt unit that may go double in size. But even, so at the 150 megawatt scale, you're kind of getting towards the smaller end of SMR plants, the way that I understand them, but they go much larger than that. And so there is a scale issue, and global production for electrolyzers is kind of at the 100 or maybe 200 megawatts scale today. So there's a large part of building out the supply chain and getting to these other numbers. And it's part of the urgency, because getting the research done to make them more cost effective so that you can go to that scale in the first place has to be done parallel. They can't be done in series. But those things are happening, and Bloomberg New Energy Finance has talked some about kind of what China has in kind of the alkaline market and how low those capital costs are. Because what I like to talk about is that electrolysis is a well-established industry if you're willing to pay $20 per kilogram for your hydrogen. If you're willing to pay $2 per kilogram for your hydrogen, which is what you need to do to become competitive with SMR, then we're a long way away. And a lot of it does have to do with scale issues as well. So there's a whole bunch of issues along the scale pathway, so it's probably enough for me.
Scott, did you have?
Well, I would say our debate is more about how rapidly these anodes costs will come down over time, and as you have a learning curve of scaling those up, how quickly will they come down? Less than the absolute size of the plant, in a way, because we get excited about having relatively small scale plants that you can locate in different places if you can get the process to work much more efficiently. So we have some, our friend Kimberly is very bullish on the cost of that coming way down and changing the economics and having an advantage of small scale compared to the big SMR plants, because you can not have to have a huge market for it. You can put it in local areas. So.
Just to throw a slightly different dimension into that is that a big portion of the cost of hydrogen is not just associated with its generation, but with the distribution. And so I think it's really important that while a lot of SMR plants have been associated with major stationary users, they are typically built very close by, or here in Texas where you have actually a very well-established pipeline system, you have a little bit more flexibility. But in a lot of locations, it's associated directly with the user. And so that is driving certain scales as well. So as we are looking at different use cases for hydrogen, the generation scale is potentially changing accordingly. So I think we have to really ultimately take a systems approach on what is the right size.
Question up here.
question for Bryan or Scott. What is the size of the hydrogen market in Houston, and what do you see as the opportunities for Houston to become a leader in developing these new applications?
Do you know the size? Okay, that's fine. It's going to be big in Houston and Texas, right? So most of this goes, so Marc had mentioned kind of the hydrogen pipeline that exists. It goes basically from like Corpus Christi through Louisiana and then up a ways into Texas and maybe Arkansas or something like that. There's 3 geological hydrogen storage networks on that as well. So there's this huge commodity of hydrogen that's running through here, and most of it's being made from methane, and it's going for upgrading oil, right? I mean, there are ammonia plants that are connected or included in that as well, but most of it here is actually for petroleum. I don't know what percentage of the refining happens here, but you can basically take 1% of the energy of the country based on hydrogen, and then just normalize that for how much of the refining is done in this area versus the U.S. totally. And that's, you know, it'll be a big number. One of the big issues for hydrogen, and this comes back to a lot of these other things, is that it really is a strong parallel to basically store and move it effectively, and the advantage that we can just leave it in the ground to store it until we want to pull it out. But there's lots of places where we either put it back in or store it in different ways. If we had that for hydrogen, it would make a difference. And we go back to some of the earlier questions on OECD countries. It's basically, if they don't have a different infrastructure, they don't necessarily have to copy ours. They can hop to what it should be instead of what pathway the rest of the developed world has gone. In places like China, especially the underdeveloped parts, it's possibly how they're going to pull kind of this forward and even potentially use it to their economic advantage to create the technologies that eventually a lot of other places will look to adopt.
So this is a segue with what both Scott and Bryan said about how sometimes smaller scale could be an advantage rather than a disadvantage. So a lot of the big energy systems are dominated by chemical engineers, and all my degree is in chemical engineering. And the first thing you do when you start developing something in chemical engineering, you think about 2 things. Can I do this as a continuous flow process, and can I do this with volumetric scaling? Because if those are 2 yeses, typically your instinct tells you it could scale really well. But you never have a way to estimate the prefactor to the scaling law, right? And there's lots of problems that they win at small scale over the processes that scale volumetrically. Is there a way we could think about this? And where do we look if we want to evaluate some of these processes as we develop processes for direct splitting of hydrocarbons into hydrogen and carbon, to get a sense of whether some of the processes that will look like they will never scale to a chemical engineer perhaps would actually work well for a situation where medium or small scale is an advantage? Where do we look for guidance?
Well, I'll start with just a comment that one of the things that we've learned in the last 20 years of kind of doing these economic energy outlook analyses is how having small scale investments can enable you to try something in a low cost way, learn from it, and then improve the technology without having to make, like nuclear, massive investments, and then you overinvest in one, you never want to do one again. Solar, a little bit, get better each time. So we're now in the world where if you are a company thinking about making investments, you'd like a small scale investment to try it and put it in place, see the economics work, knowing full well that the next one will be lower cost. So if we can find ways to take these technology, try them in one place, learn from it, come up with another one that is a bit lower cost, rather than have these big mega investments, to try things at scale, that you'll go down the learning curve faster that way. So that's one of the things we've learned.